A common point of confusion in exams is the differences between series and parallel circuits. In a series circuit, we only have a single loop, and the components are all connected one after the other. On the other hand, parallel circuits contain more than one loop, and this small difference completely changes how we measure current, voltage, and resistance. In this video, we'll discuss series circuits and some of the calculations that you might have to do. Then in the next video, we'll consider parallel circuits. So with this series circuit, because all the components are in a single loop, if any one of them is disconnected or broken, the whole circuit will stop working. This is a really big downside, and so in practice, very few things are actually connected in series. Another thing to know is that the potential difference of the cell or battery is shared across all of the components. You might sometimes see this shown as an equation like this, which just shows that the total voltage is equal to the voltages across all of the individual components. So the first component plus the second component, and so on. So if our battery here had a potential difference of 12 volts, and the only components are these two lamps, then the voltage across the two of them must add up to 12. For example, if these two lamps were slightly different models, and the voltage measured across one of them was 8 volts, then there must be 4 volts across the other one, as 8 plus 4 is 12. Whereas if both lamps were identical and had the same resistance, then the voltage must be 6 across each of them, because they would each get half of the 12 volts. Current, meanwhile, is the same everywhere in the circuit, no matter where you look. We measure current using an ammeter, which we place in series, so within the main loop. And because the same current flows through all of the components, we can put the ammeter anywhere. For example, instead of putting it down here, we could put it up on one of the sides. It really doesn't matter. We could also calculate the current by dividing the total potential difference by the total resistance, which is just a rearranged form of Ohm's law. Resistance is similar to potential difference, in that the total resistance is just the sum of the individual resistances of each component. This green symbol just means sum, so total, and you sometimes see it in physics and maths papers. As an example, let's imagine that this lamp on the left had a resistance of 4 ohms, and the other one had a resistance of 2 ohms. The total resistance of our circuit would have to be 4 plus 2, so 6 ohms. Now that we know the total resistance of our circuit, we can use Ohm's law to calculate the current by taking the potential difference of our battery, so 12 volts, and dividing it by our total resistance of 6 ohms, to give us a current of 2 amps. One thing to be aware of is that ammeters generally have such tiny resistances that we can ignore them in our calculations, which is why we haven't included anything for the ammeter. The next thing we need to look at is how to calculate the voltage across a single component in a circuit. We just worked out that the current in the circuit is 2 amps. And remember that with current, it doesn't matter whether you're looking at the circuit as a whole or at an individual component. The current is always the same. So we can use that current and the resistance of a specific component to find its individual share of the voltage in the circuit. For example, this lamp on the right has a resistance of 2 ohms, and the current across it must be 2 amps. So using our Ohm's law equation again, we can see that the potential difference must be 2 amps multiplied by 2 ohms. So there must be 4 volts across this specific lamp. To find the voltage across the other component, we could do the same thing again, or because we know that the total voltage must be the same as the battery, which was 12 volts, we can just do 12 minus 4 to find that this other lamp must have a potential difference of 8 volts. Or if you don't like maths, the final way we can find the voltage is just to use a voltmeter, which we connect in parallel across the component we're looking at. So this one would give us a reading of 8 volts. Even though voltmeters are in parallel, we'd still treat the overall circuit as being series. As a final point, it's good to remember that due to Ohm's law, those components with a greater resistance will always have a higher share of the voltage. You can think of this in terms of more force being required to push the charge through the areas of highest resistance. This is why our 4 ohm resistor had 8 volts of the overall potential difference, but our 2 ohm resistor only got 4 volts.